Fix number 1. Here we go.
Make a new rule. If it's raining, we all just get to stay home. Just watch movies all day.
You're gonna make that rule?
What?
You're gonna make that rule?
I probably have to get approval from Todd or somebody.
We'll just do class online.
There you go.
Just do like a recording. You can be at home and just record it.
Yeah, I'll just lay in my bed.
Yeah, and then everyone just log on, and then they can email you questions. Just record it and send it to your email.
Yeah. I'm sure that would work.
And then group participations, and we have like a discussion board going. Hey.
So where are we on 20 here?
Whatever. Yes. Okay. Yes.
I think we're on cardiac cycle.
Yeah. I was just gonna say because we never even got papers for a group
Yeah,
assignment thing.
that is true.
And then he didn't want to start into this because he said it's all kind of related. And then
Yeah, we only had like 4 minutes.
Yeah.
Like,
he said, why about this?
All right, so we are on cardiac cycle then. Did everybody go home and dream about heart steak? All right, so we are on cardiac cycle then. All right, so what is cardiac cycle? Heart steak. Basically, it's one contraction of the atria, one contraction of the ventricle. That's one cardiac cycle. In relaxation as well. And there's all kinds of things going on in the heart, right? There's electrical stuff, which is the signal to contract. There's changes in pressure in all the chambers. And of course, blood's moving, so volume's changing. What do you think mechanical events is talking about? What sort of mechanical things are happening? Just the signal to contract. Yeah, so those valves are opening and closing. That's what they're talking about for the mechanical events. So volume's changing. And what's kind of interesting about it is they're all kind of related. Because what causes those valves to open and close? Interesting about it is they're all part one kind of related. Right? But in general, is it like an electrical signal?
Pressure.
So it's a pressure change, right? So the pressure change determines like when the valves open or close. And if the valves open or close, that changes how much volume is in each place. So it's all kind of related. So we'll try to put it all together. Right, so I'm actually going to not have you fill in the table yet. Do something a little bit different. All right, so this will kind of put it hopefully all together. So we'll skip the electrical, do the phases here.
Initiates the cardiac cycle.
Oops.
Phases that follow are isovolumetric contraction, ventricular ejection, isovolumetric relaxation, and ventricular filling.
Anyone know what that isovolumetric word means? Any guesses?
volume stays the same?
Yeah, it does. So first the atria contract and push more blood into the ventricle, and then the ventricle starts contracting. But does that aortic valve open right away? It has to build up some pressure first. So that's like the contraction without the volume of blood changing. So I just call it isovolumetric. Not something you really need to know, but once the pressure builds up enough, pushes that valve open, and you get ejection where the volume goes down. And then it relaxes, it fills back up with blood. So we'll keep going here. Click on the heart. Okay.
Prior to atrial contraction, the atria and ventricles are relaxed.
All right, so it's kind of crazy. There's a lot of graphs up there. We're not going to worry about the EKG one too much, except to remind us what's happening right here in this pink one, this pink bar. Do you remember? Yeah, so it's atrial contraction. What's in the blue here? Ventricular contraction, and then this one, relaxation. So they just put that up there so you can kind of know, what part of the cycle you're in. And then this graph is telling you the pressure. And all we're going to worry about is the ventricular pressure, which is in what color? Blue there. So just worry about the blue line here so you can see how the pressure changes. And then down here is the volume of blood in the ventricle. So just worry about the blue line in the middle and then this volume line down here. And you can see how it's kind of changing during each of these phases. Look, I have a secret message. I'll look at it later.
Lunar valves are closed. The ventricles fill with blood. Depolarization triggers atrial contraction.
Right.
Contraction increases atrial pressure and pushes extra blood into the ventricles, slightly increasing ventricular pressure. The excitation triggers ventricular contraction.
All right.
Ventricular contraction is at first isovolumetric. This means that ventricular blood volume and muscle cell length do not change. Contraction causes ventricular pressure to rise above atrial pressure, forcing the AV valves shut. With the valves closed, the continuing contraction increases ventricular pressure.
Where's my table? All right.
Ventricular ejection takes place when ventricular pressure rises above arterial pressure and the semilunar valves open. The valves stay open for about a quarter second. As blood is ejected into the arteries, ventricular volume decreases. Ventricles begin to repolarize and relax. Ventricular pressure decreases and contraction ends.
All right, and we've got our relaxation phase.
Repolarization of the ventricular muscle cells initiates isovolumetric relaxation. As the ventricles relax, pressure in the ventricles drops. Semilunar valves close, preventing backflow. The closure produces a dichrotic wave on the aortic pressure curve. With both semilunar and AV valves closed, blood volume does not change. This isovolumetric relaxation sees pressure drop quickly. Ventricular filling occurs as all four chambers of the heart are relaxed and the AV valves open. As the valves open, the ventricles begin filling with blood. In about 0.2 of a second, blood that has been building up in the atria rushes in to fill the ventricles. Atrial depolarization triggers atrial contraction, forcing a small amount of extra blood into the ventricles. And a new cardiac cycle begins.
All right, so we're going to try to do next is fill in this table for atrial systole, ventricular systole, and relaxation. And you're going to tell me what happens to the volume in the ventricle, the pressure, and the valves are open or closed. Some of them might be closed, then open, open, then closed, up, then down, whichever. And you can use those graphs to help you. So we'll try it, give you a little bit of time just by yourself. Yeah. I'm going to get back to this. All right. Oh, you can't use your book either. All you could do is look at that graph for now. And I bet you could figure it out, or at least come close. Or at least just think about it. And just in case you're getting stuck, pink is atrial systole. I guess that's purple. And then blue. I just wrote relaxation. And then that second graph down, that blue line, is the ventricle pressure, ventricular pressure, which is the only one we're putting on the graph there. Yeah, LV is left ventricle. So you're basically just reading that graph. That's what you're doing. You can do it. Even if you get it wrong, at least write something down. Just make yourself write something. So Alex, what's happening? What's happening on the graph alert? And for the volume when it's atrial systole? It's in pink, right? For pressure, but the black line's the volume. See? I didn't have to tell you anything. You already knew it. Oh, you just have to put like increasing, decreasing, increasing, then decreasing, not changing. That's what we're talking about for this. So what do you think for this one? Right? All you did was read the graph, right? It's easier than you think. Yeah, so I think those would be right. I guess for the pressure, is it changing at all, relaxation? The red line? Or the blue line? Sorry, it's the blue line. Really? In the blue area? Uh-huh. Yeah. You're right. All right, so what do you think for this first one? This one's the volume graph. I should probably write this. All right, so maybe you want to work with your group to finish those. See if they got the same thing as you, etc.
See, I wasn't sure 100% if that's referring to like pressure building up or the pressure falling down after all the fluids you did.
Well, you might have to write more than just one word for that one, right? To describe what that line's doing.
So we go up for the volume, it decreases in the purple area.
Okay, yeah. I mean, it does. Yeah, because it's a straight line.
I would say, just for you, with a, like, which way it does change. That's it.
It doesn't, in the atrial, it doesn't change, it's flat in the pressure. See how it's flat? I mean, it's high. Oh, it just goes up a bump, I mean. See how it goes up, but then it spikes. So I said it increases a little until your ventricular.
She's right.
Then it jumps. So the next one is when I said it jumped a lot, like underneath it. Because they're different. We're on the pressure one, the graph in the middle. Which color are you looking at? Blue. Okay. See how the blue bumps a little?
Yep.
Yeah. So even if we say pressure changes.
Are getting it, you think?
Yeah.
What's that say? Oh, you're gonna finish writing increase. I'm like, in? What?
Because the mitral valve,
But not like nearly the second spike.
getting increased, right? Because it pushes it up.
It closes the mitral valve.
Okay, wait, we have
Okay,
it backwards.
backwards, yeah.
Yeah, I did.
Because you don't want, when the pressure builds up, you don't want the blood going to the atria, right?
Right.
It's the aortic valve that opens.
Okay, that makes sense. Well, in the atrial systole, when it contracts, the mitral valve is obviously opening because the atrium is contracting. And your aortic would be closed.
And then it opens.
But during the
Which valve? Which
the
one?
mitral valve.
In atrial?
Yes.
It's open.
And then,
Always?
yes, because your atrium.
Well, it doesn't close until the ventricle pressure builds up.
Yeah. And then they would
Which is
flip.
interesting, because I know what you're thinking. You're thinking it stays closed till the atria pumps it, but it's actually open during relaxation too.
Oh, really? I didn't know. I did, I supposed to too.
How does pressure build up?
It doesn't really, not very much.
It really
Why
just
does the
builds.
atrium even need to contract, really, if it can flow on there?
So like, well, we'll talk about it in a second, but blood comes into the ventricle and the atria at the same time, and then the atria contracts to push a little more blood into the
Just rest of it
ventricle.
that didn't go through.
Which is weird because that's not how we think of it. You think of it as like from here to here,
Yeah. Okay.
but we're going to talk about it all together.
Okay. So then, relaxation. Side foot close. But it's open. And then I think you can relax in the aortic system.
Are we still looking at which one are we looking at?
I just went to.
Am I getting them all, you think?
Yeah, but for this one, what line, what color are we looking for on that middle one for the pressure?
It's the blue line, the ventricle pressure.
Yes. Okay. Yes.
So it increased,
Yeah.
so it increased, right? Yeah.
And then what?
Because your pressure.
It increased.
And then
Uh-huh.
Because your ventricle is stable, and so that's where it confused us.
For the aortic
Yeah,
valve,
mid it
I'm
drops.
Yeah.
confused as whether like if the mitral valve is open, if it closed, is it always opposite? Or can it be both open and closed?
I think they're pretty much always
Yeah,
opposite.
because you're starting to go into relaxation phase.
So in relaxation, well, let me ask you, what opens the aortic valve? What makes it open?
And then open.
Which kind of pressure change?
Close, then open. Yeah. Okay.
Mhm.
Do relaxation.
So do you think there's high pressure or low pressure in the ventricle during relaxation? So is that valve open?
no, it's closed.
There you go.
I just didn't know how
It starts to begin to go, and what I said is, it gradually goes up to hit around the starting point and,
Oh, I thought you were asking me about the aortic valve.
Oh,
get back into
okay,
your.
I'm close to that one.
Yeah, so the other one's open. Because they're opposite. So you got it right.
So we just, like basically focus on the pressure
Drops
of it?
back down.
Right, because that's what opens and closes those valves, right?
So,
I said it drops back
so
down.
if this one increases, then it decreases.
Because it goes back to
Does it mean it
when it begins and
ends
it
up being
comes
closed?
It'd be closed,
So then,
then open.
Yeah.
Closed and open?
Mitral valve, like when she was asking, I would have thought.
Right? Because what makes it open? The pressure going up, right?
About it as like.
So it's open and then closed?
Sorry, open and then closed. Yeah, that's what I should have said. I said it backwards.
But really, it's just a contraction, it screws up just a little bit, that didn't make it through.
All right, did you get all those valves, you
You know,
think?
that might be caught up in the little corners or something. Yeah. Which adds exactly like Carl's. Yeah.
All right, where's my extra one?
It was contracting through the vesicle. So it would have to be open.
Do you have any extra ones? Am I crazy?
I was thinking of it building up pressure. And then.
Oh, here it is.
Yeah, and that's exactly, and that's what I was thinking, but I wasn't thinking it would open. Really, I didn't know.
All right, so y'all are doing great. Let's make sure you got everything on there. This is good practice, like reading graphs, because there's so much information up here.
Yeah.
But I think if you could read a graph, kind of work on it, it's a lot easier than reading like 10 pages of the book about the cardiac cycle. Because everything you need to know is right there in those 2 lines. All right, so let's go, let's just go top to bottom. I think that's easier. So atrial systole, what happens to the volume? It increased, right? Ventricular systole, what happened to the volume? It decreased. And in relaxation, what happened to the volume? It increased. And then the pressure, atrial systole, what happened to the pressure? It increased a little bit, right? This blue line went up a little bit in the pink area. What about for ventricular systole, what happened to the pressure? It increased and then decreased a little bit. So it's increasing a lot and decreasing a little bit. And then relaxation, what happens to the volume or the pressure? It decreased, right? What's next? All right, the mitral valve. Before we talk about the mitral valve, what causes the mitral valve to close? What kind of pressure? High pressure where? In the ventricle? Well, it could be at the atria or something, I don't know. So that means you basically look at this graph. And we start at atrial systole. Is there high pressure in the ventricle right here? No? So is that valve open or closed? Open. So you just told me it closes when there's high pressure. We're talking about the mitral valve, the AV valve. What about in ventricular systole? Does it close? It does, because we have high pressure. And then what about during relaxation? It's open, because right, the pressure's pretty low quickly. All right, and then aortic valve. You could just do the opposite of the mitral valve, or you can think of what makes the aortic valve open? High pressure in the ventricle makes the aortic valve open. So over here at atrial systole, is there high pressure in the ventricle? So is that valve open or closed? It's closed. What about in ventricular systole? Right away? It's closed, then open. So pressure's increasing, and when it gets to its highest pressure, that's when the valve opens. That's what makes it open.
So can you just go back up the atrial systole? So the mitral valve is open?
Yes.
So the aortic valve is closed.
The aortic valve is closed during atrial systole.
Pressure increases and the aortic valve is open.
Uh-huh. Yeah, so, sorry, for the aortic valve, it's closed and then it's open in ventricular systole. I would put closed, then open. Because it doesn't open until the pressure gets at its peak point, right there. That blue line gets to its peak.
Yeah. Yeah, what about the atrial systole? That's what
Oh, this one? It's closed. The aortic valve is closed.
And the mitral valve is open?
Yes.
How is it closed?
Yeah. Yeah.
Which valve? The aortic valve? It's not high enough to open it.
No.
Because when we were going over it, you said the mitral valve was closed and the aortic valve was open because the volume or the pressure was increased.
Yeah.
So
Yeah, I'm just confused. You told us one thing and then you said another.
I think you thought we were talking about the different valve or something, because we were talking about all the mitral valve stuff already, and you wrote it all down.
Yeah.
And then we just started the aortic valve. All right, let's just double check. So mitral valve, let's go back to mitral valve, make sure everybody's got it. So atrial systole, it's open, the mitral valve. And then ventricular systole, it closes, the mitral valve. So there's pressure building up. And then relaxation, the mitral valve is open. So that's the mitral valve. And
So
then
if the pressure is increasing, does that mean it's open or closed?
for the mitral valve,
Oh, so it's
right? So the mitral valve and the aortic valve, they function oppositely. So when there's high pressure in the ventricle, like right here, the mitral valve is closed and the aortic valve is open. When there's low pressure, the mitral valve is open and the aortic valve is closed. Right? Mm-hmm. And the mitral valve is closed. Uh-huh.
Because it's going down.
I'm just going up and down.
I know, but we just have like.
That's right. I'm practicing. We're gonna get, and we're gonna talk about it all together. Let's just get this table filled out, and then we'll do one little review of all of it together. So this is confusing. All right. So aortic valve. So aortic valve. Atrial systole.
Closed.
It's closed because there's low pressure. Ventricular systole. It's closed, and then it's open.
Oh, so it's closed and then open?
Yeah. Because until the pressure builds up all the way up there to 120, it stays closed. Then it's open, and then relaxation, it's closed. All right, so kind of talk about it all together. Maybe we'll start, I think it makes sense to start at relaxation over here. So relaxation, this valve is open, the mitral valve, and both chambers of the heart are filling with blood. The blood's coming back from the vena cava or the pulmonary veins. It's filling up the atria and it's filling up the ventricle. You may have in your head that it just comes to the ventricle and sits there first. That's not really how it works. And you can tell because this line is telling you that the volume of blood in the ventricle is going from like 60 up to like, I don't know, 110 or something before the atria contracts at all. And that's because this valve is open, blood's coming to both of them. And then when the atria contract, it pumps a little bit of extra blood down to the ventricle through that open mitral valve. And that's why you see this little bump of blood volume go up. That's when the atria contracted and pumped the extra blood in. But it's not even that much more, right? It's kind of interesting because it went from empty was like 65. Before the atria contracted, it's like 110 or something. And then it just goes up to like 130. The atria contracted. So it puts a little bit of extra blood in. And then when the ventricle contracts, that pressure makes the mitral valve close. The pressure building up in the ventricle. And then it contracts more, and enough pressure builds up to open the aortic valve. Does all the blood leave then? So it's about half, right? That's about right. That's what's called your ejection fraction. It's what percentage of blood leaves. You can change that with drugs, with exercise, heart failure drugs and stuff. But, that's only about 50% of the blood leaves. So I like these graphs because I think it really kind of shows you what's actually happening, which is different from probably what you imagine in your head is happening. Because you'd think all the blood leaves and yada yada, but none of those things actually are true. All right, what other questions you got?
So the pressure when we were looking at that blue line, right?
Yeah. Yeah. And on the study guide, the pressure and volume changes that occur in the cardiac cycle is just talking about in the ventricles. So you're going to add that somewhere. The study guide thing, the pressure and volume changes, just talking about the ventricles. So basically that table you filled out. That's what we're worried about. Yeah, I'm not going to ask you about the atrial changes. atrial pressure or anything, just what's happening in the ventricles.
That
So
was J.
that was, yeah, it's J.
So just kind of know this chart.
Yeah, it's the chart you just did.
Okay.
Which one?
So, this is where I'm kind of lost. It's like, what you were saying is like, if the pressure is increased, the aortic valve can be open.
It has to increase like above, it has to increase up to like 80 or 100. So that little bump here isn't enough to make that mitral valve close. So it's not so much that it's going up, it's like how high it is.
Also, it depends how much pressure.
How much pressure, yeah. So in case anyone else is confused, say just figured something out. So that mitral valve, it has to get to a certain amount of pressure to close. And this little bump isn't enough to close it right away. Right, it has to get up to, 80 or something to close it. No, that was where they were getting stuck and why that wasn't making sense. Maybe that's true for other people. All right, so I think if you're having trouble with this one, first thing to do is make sure you know the order of blood flow, which are, those cards that you've got. Because if you don't know which way the blood's going or where the valves are, is this going to make any sense? Probably not. And then the second thing you got to make sure you know is what makes those valves open and close, like what we did last time. So make sure you know those before you try to figure all this out.
If you put, let's say you put that chart on the test, you wouldn't put like that on there either, would you?
This?
Yeah.
Um,
Would you kind of just leave it like that and just?
Probably not, because you should know the EKG thing, right?
Okay.
That was one of the other study things. So that's atrial, that's ventral, that's relaxation. So yeah, it could just be these three charts. What else is on here? All right. All right, so when during that cycle do the ventricles have their maximal amount of blood? Sorry, space. Remember, systole's contraction, diastole's relaxation. All right. So why don't you talk to your neighbors there, and then we'll vote again.
Sure, but it wouldn't be maximum. No, because the loss of the fit is pushed to the atrium. Okay, that's what I was like, I was trying to see, if you might be right. So that's what I thought. Yeah, like looking at it, that's, yeah, okay. Yeah. It is what it is, right?
All right, anybody else? Let's see what you got. Up to 70% for B, which is the correct answer. We got a few for A. At the end of ventricular systole, that'd be the lowest amount of blood because it pumped it out. Right. I guess we'll let you back in. And you could see that. So at the end of atrial systole, that's when the volume's at its highest. At the end of ventricular systole is when it's at its lowest, right here. All right. We did that already. Is there anything else on that assignment? That's it, isn't it? All right, good. All right, so the next challenging thing is cardiac output. So that over here. So cardiac output is equal to stroke volume times heart rate. And just to make it make more sense, the stroke volume is milliliters per beat, and heart rate is beats per minute. So what do you think the unit is for cardiac output then? Right, so these kind of cross out. So that means the stroke volume is how much blood is pumped in one cycle. The heart rate's how many times the heart beats per minute. And so cardiac output is how much blood is pumped every minute. So that means if you want to change how much blood your body gets, what's the two things you could change? You could change your heart rate, or you could increase the stroke volume. And that's basically what we're going to be looking at, is how you could change those up or down, those two different variables.
Action of the heart maintains blood flow throughout the human body. Cardiac output is a measure of blood flow. It is the volume of blood ejected from the heart over a given time. Cardiac output is determined by multiplying heart rate by stroke volume. Cardiac output in the typical resting heart is about 5 liters per minute.
5 liters a minute, so it's like 2 liters of Coke or something more than that every minute. Pretty crazy. Especially if you think about how much space was in those ventricles that you dissected yesterday. Not a whole lot. And something I mentioned to a few groups, I think, when that animal died or whatever, rigor mortis, so that's like as contracted as the heart could get. So that was it during like the end of systole, that space. So when it filled up, it would actually be, the chambers would be bigger than that. All right, so let's see what happens if you exercise.
Cardiac output is not constant. It varies with the body's metabolic demands. Mild exercise will double cardiac output, while an intense workout can increase output as much as 4-fold, to 20 liters of blood each minute.
So what changed for exercise? Yeah, so both of these went up, which is going to make cardiac output go up too, right? And of course, kind of the reason the heart works that way is you don't want to waste energy pumping extra blood all the time, but you need to be able to increase blood flow if you have to exercise or run away from a tiger or something. So it's kind of set up to have, is that on there somewhere? Cardiac reserve. I don't remember if it was on there. Yeah.
Yeah.
So that's what cardiac reserve is that the heart can beat faster and harder when needed. Which is good, because otherwise you'd try to briskly walk, and you'd be out of breath in like 10 seconds. Be like, oh, I can't do it. Which would not be a good way to have it. All right.
Stroke volume is directly correlated with cardiac output. The greater the stroke volume, the greater the cardiac output. Stroke volume represents the difference in the amount of blood between the volume in the ventricles at the end of diastole and the volume after systole.
So basically, right, we said it's how much blood is pumped out, which means it's how much blood was in there at the end of atrial systole minus whatever's left over after it contracts, is all they're saying. Just with fancier words. I guess I should write it. Or if you remember on that graph, the volume graph would be the difference between the highest it got and the lowest it got. Would be stroke volume.
Three factors increase stroke volume: increased preload, increased contractility, and decreased afterload.
And that's on a slide in a little bit. So 3 ways to increase stroke volume. Higher contractility, higher preload, or decreased afterload. Let's see how those work.
Preload is the degree of stretch of cardiac muscle cells prior to contraction. The amount of stretch is related to the end diastolic volume. Increased return blood flow from the veins increases end diastolic volume. Cardiac muscle sarcomeres stretch and lengthen. Contraction of the cardiac muscle sarcomeres during ventricular systole provides the force to eject blood from the heart.
So increased preload is increased diastolic volume, which is the amount of blood that comes into the ventricle. So if you have more blood coming to the ventricle, do you think you're going to pump more out of it? Or at least the same amount? So for example, we said, before the diastolic volume was 130, systolic was 60. If you have more coming in, like 150, and you still have 60 left, you've pumped more blood, more volume. That's all they're saying. Increased preload is more blood coming to the ventricle, which means more gets pumped out. We'll skip that one. All that. All right, what about contractility? Oops.
Contractility is the forcefulness of cardiac muscle contraction. Inotropic agents can increase or decrease contractility at any given level of stretch. Positive inotropic agents increase contractility, thereby increasing stroke volume and cardiac output. Negative inotropic agents reduce force of contraction.
All right, so let's just talk about the positive inotropic for now. If you're increasing contractility, do you think you're changing the diastolic volume or the systolic volume? Systolic, right? So that means, is it going to get higher or lower, the systolic volume? Because you're pumping, the heart's going to, instead of going this far, it's like going this far. It's like just contracting more. So there's going to be less blood left. I know there's kind of a lot of math going on here, but if you decrease systolic volume, what happens to your stroke volume? And if stroke volume goes up, what happens to cardiac output? It goes up. So if you can memorize that equation and this equation, you can pretty much figure all this stuff out without having to memorize a whole bunch of stuff. That's just 2 little equations to memorize. Just 2. I'm in math, you have to memorize like 100, right? Or are they nice and let you bring in all your equations on note cards or something?
I'm taking it online.
Yeah. And then you have your book.
It's all like the apothecary stuff. Could be easier, Google.
All right. And last, decreased afterload.
Afterload is the pressure or force that the ventricles must overcome to push open the semilunar valves and eject blood. Blood pressure in the left ventricle must overcome arterial pressure in the aorta in order to open the aortic valve.
So here's our little graphs here. So when the ventricle pressure gets above just the blood pressure that's in the aorta, that's when the valve opens. So we'll keep going.
Hypertension increases aortic pressure.
Okay, let's go to this one. All right, so I don't want to talk about that one because that's the opposite. So a decreased afterload means there's less pressure to push against. So which of these do you think is going to change? There's less pressure. It's easier to get the valve open. Sorry, it's easier to get the aortic valve open. It's the systolic then. If it's easier to get that valve open, more blood's going to leave the heart. Which means we've got decreased systolic volume again. So there's those 3 things. You could also flip it all around, right? So if you decrease contractility, you're going to increase systolic volume. Everything's backwards. Because all these things could go in either direction. We just chose the 3 that increase stroke volume. But we could just as well turn all these arrows around and have it decreasing stroke volume in the other direction. So let's back to the old PowerPoint here. Oh, how about some math? What's the stroke volume of a patient with a heart rate of 60 and a cardiac output of 600? All right. So it is 10. All right. Because heart rate 60, stroke volume's like X, and then 600. So it's 10 times 60 equals 600. Right. So here's some examples of what we were talking about. So one thing, preload, if you have increased blood, like overall blood volume, then you're obviously going to get more blood coming to the ventricle, right? So one example of that is during pregnancy, blood volume increases by like 30%. So the heart's actually working. It's going to pump more blood. Makes sense, right? You need a little bit of extra blood for that creature. Because you never know. Like, it could just come out like that alien in the Alien movies. Sorry. So you did watch that? Yeah, I would not. I did not watch that when my wife was pregnant because I didn't think I could take it. It's terrifying. Doesn't it like eat its way out, or they cut it out?
She cuts it out.
She cuts it out.
Eat its way out. And then she turns and tries to eat her.
How did it get in there?
Her and her boyfriend, fiance, whatever, did the dirty when he was infected. Yes.
Oh, when he was
turning
infected.
into something.
Oh, right. So it's like in the sperm or something. Little alien sperm. Yeah, it's crazy. All right. So contractility, that just means, for the most part, it's like certain drugs you take, like epinephrine or, what's another one? Can't afford that one. That one's a pretty intense one. And it's kind of weird because if someone's in heart failure, sometimes they get something that increases contractility, and then sometimes they get something that decreases it. It just depends on how bad their heart failure is. Because if their heart's like barely making it and almost out of oxygen, if you give them something that increases it, it makes the heart wear out faster. It's kind of weird how that works. So, and then afterload, and there's also heart drugs that decrease contractility, so the heart doesn't have to work as hard, which can conserve the muscle for a while. And then afterload, more pressure, so that would be increased afterload. Like if your arteries get narrowed, your blood pressure goes up, and that would decrease the stroke volume if you increase the afterload, because there's more pressure to push against, so not as much blood leaves the heart.
So you know how you said that if we made it opposite, so if contractility went
Down?
down,
Uh-huh.
would that increase systolic volume?
It would. And then that would decrease stroke volume and decrease output. So probably the best way to think of these on a test or something is write these two equations and just, do it step by step. Like what happened to the volume? Because if you think about it, if the contractility goes up, well, you're pumping more blood out. If it goes down, you're pumping less blood out. Like it's pretty logical if you kind of take it little bits at a time. I don't really like this question. Let's just ignore it. So just ignore that question because I don't really know what it means. I wrote it, but now I don't know what. I'm not sure what I was thinking when I wrote work harder. I don't even know what that means. So just ignore it. All right, what about exercise? Or I guess first, do you have any questions about stroke volume, factors? All right. So just a few slides about exercise. And this is actually one of the understudied things about the heart. It's like our lab at CU is one of the few labs that was like actually researching what exercise does. to your heart. And short term, pretty obvious, your heart rate goes up, your stroke volume comes up, because you need more, blood flow everywhere. And then in the long term, so something like, you're doing aerobic exercise like 5 times a week, something like that, for like 30 minutes or an hour. It actually makes your heart get larger, and it's able to pump more blood with the same amount of beats. Because, which of these things do you think changed if your heart muscle gets bigger? Yeah. So that training, like someone who's swimming a lot or running or walking a whole lot, their heart muscle gets bigger, contractility goes up, so their stroke volume's higher. And so that means, that they're pumping more blood every beat, which is kind of cool. How much do you think, what percentage weight gain do you think from in mice at least, 2 weeks of exercise on a mouse? What percentage do you think did it increase? The heart rate. What do you think? It's not usually quite that much. It's 15 to 20%, just in 2 weeks. People aren't quite as dramatic. It depends on how much exercise you do. And this is thought to be incredibly healthy for you, because if your heart beats less, is that good for it?
Yes.
Right? So less beating, less damage. So I think that's one of the big benefits of endurance, like any kind of aerobic exercise. All right, why does exercise reduce your resting heart rate? All right. So it is D there. All right. Increases the stroke volume, and it's able to pump more blood with each contraction. So it doesn't need to contract as often. And so for extreme, what's average, 60, right? 60, 70. So people that do ultra marathons, we had 2 guys that we worked with that, did the Leadville 100-mile race. And their resting heart rate's 30, or 25.
My mom,
Which is totally crazy.
because she had chest pain one night.
Uh-huh.
So they were watching her overnight in the hospital.
Uh-huh.
And my parents work out religiously, but her heart rate dropped to 32 in the middle of the night. And they were all freaking out.
Wow. So how much do they exercise, would you say?
6 days a week.
Yeah, for an hour or something?
Yeah.
It's a lot of exercise.
That's where my brother gets it from.
And you exercise all the time too, right?
Yeah, 3 days a week. I'm working before.
3 days. You're walking around. That's good. All right, so we'll do a little bit of 21, and then we'll take our quiz next week. Then we have our test on Thursday. Dum, dum, dum. Where are we? All right. And this is all pretty related, because one of the big factors for blood pressure is cardiac output. Because if you're pumping more blood, what's going to happen to your blood pressure? It goes up, right? So 21 is very related to the heart. So you'll see a lot of the same stuff. Did I put that in here? Weird. All right. I thought I wasn't going to teach this part. Oh well. So anyways, you can think of, the aorta as like your largest artery because it's got all the blood coming out of the ventricle. And then you just think of it as branching into smaller and smaller branches, like you're irrigating the body. So you've got a big tube, and then it just separates into littler and littler ones. And the biggest ones are the elastic arteries. They have lots of elastic fibers, so they can take that high pressure without breaking, and can expand a little bit and come back to the original shape. And then as you get to the smaller ones, they have more smooth muscle and fewer elastic. And what do you think the smooth muscle's for? It's to do what? Yeah, so if you want to control how much blood's going somewhere, you dilate and constrict, which that's smooth muscle contracting and relaxing. So that's where you kind of decide, okay, let's not send blood to our feet. Let's contract the smooth muscle in that area. Or like now, because everyone's thinking so hard, it's dilating to send more blood flow to your brain. And I was actually reading something yesterday. They did some studies about like exercise and blood flow to the brain. Like exercising 3 times a week, like leads to constant increase in blood flow to your brain, even when you're not exercising, like the next day. Yeah, and that's why they think your memory works better when you exercise.
It's not, there's been studies that show that it's not people who do like a bunch of crossword puzzles that help them from getting dementia. It's people who keep their bodies moving.
Yeah, definitely. All right, and then as you get smaller and smaller diameter, right before you get to capillaries is the arterioles. Very small diameter. Those layers are really thin. They're small vessels, and they have a few layers of smooth muscle. So they can also constrict and dilate some. And then we get to our capillaries, which of course, what happens at the capillaries? So gas exchange, nutrient exchange. This is where, and basically you have capillaries everywhere. Like all your tissues have capillaries all over them. All right, and one thing about them that's important is, first of all, what kind of epithelial cells are those? Simple squamous. Of course, Michelle has an advantage because she just learned that in 201. So they're simple squamous, which means they're flat. So it's really easy for oxygen to get out of the blood through those cells. And then CO2 to come back. And of course, all the other substances as well, like glucose and hormones, all that business. There's a lot on this slide, but all I really wanted to show you is here's like the arteriole coming through, and then it branches into what's called the capillary bed. And in 3 dimensions, that capillary bed's going to be all throughout your tissues, like your muscle. Like it's all spread through it so that all your cells are close to capillaries. And then, of course, what do capillaries form back into? They're going to make veins. Because you take the oxygen out, now you need to send it back to the heart. Which chamber of the heart does it go to? Low oxygen blood? The right atrium. All right. So which of these is an important characteristic of capillaries? All right, so maybe chat with your group then we'll vote second time.
The only reason I asked the question, if I were to change it, I didn't know for sure.
All right, final vote. All right, so the 17% of you that chose E are correct, which I think we had a higher number the first time. So the difference, so it's B and D. So it's good that blood flows through them slowly. So you have time for all that gas to exchange and the nutrients to go in and out, the waste, all that business. They do have thin walls, which I think everyone was agreeing on. Change diameter, though. Capillaries don't change diameter, really. It's the arteries before them, the arterioles, or the muscular arteries that change the blood flow amount. So you're changing it up here. You know, you'd cut off, squeeze this vessel a little bit if you want less blood to go into the capillaries. So what if it's bad, what does it do? Just stays white? Stays white for more than 2 seconds? Huh, interesting. So I think if you were cold then it would take longer, right?
Yeah, warm up my hands. Because I have to do that when I'm doing my cardiac assessment. So
Just warm some hands.
I always have to hold my hands for a little bit to warm them up. So the doctor will be worried.
Yeah. All right, so we're just going to do a few more slides. So you've got different kinds of capillaries in different parts of your body, and basically their differences are what the wall is like, and of course how much stuff can get through. So the first one is continuous. This is probably what you would think of as a capillary. Do you see many holes or anything? So there's not extra holes, so the only things that can get through are things that can move through cells easily, like oxygen gas, CO2, or things that these cells, you know, have channels for or something. They're the most common, so you have them basically everywhere. So these are the kind that like deliver oxygen and get CO2 out of your tissues. And the next one, what do you see about this kind of capillary? So there's actually holes within the cells, which is kind of bizarre. But there's the little pores to let some smaller things through, just directly. Can cells get through? Based on that picture? Right? So look how big that red blood cell is compared to those little holes. So you can let like large proteins through, but you're still keeping your blood cells in the capillary, which is probably a good thing. So where do you find these? So your kidneys have those, your intestinal tract has those, because it lets you get faster transport and larger solutes through. So if you're absorbing, down here in your GI tract, you're trying to absorb all that water, all those nutrients. So you have these fenestrated capillaries around the intestines. All right. And last, this one looks all kinds of messed up. So there's actually huge holes in the basement membrane and the between the cells. Those are called the sinusoid. What do you think is going to get through those? More stuff. So even very large proteins can go right through. It basically doesn't hold any proteins in it at all. So the liver has them, the spleen, and the bone marrow even. Right. So that's that. So next time we'll do some stuff with veins and blood pressure. Sweet. So Tuesday's 21, Thursday's test. Yeah.